the microphone working? Yeah. Hello. Yeah. Hello. Thank you very much. Thank you very much for coming, and sorry for this technical difficulty. So I'm here to present you the two things. First thing is the TurboGeth is the project that is been going on for a while, and it's also related to another thing which we've been talking about today, just stateless Ethereum. As I tried to show on the slide, so on the left there's a logo, the new logo of the TurboGeth. There's just a little rocket with this sort of diamond styles. And on the right, there is no official logo for the stateless Ethereum yet, but that's what I found, that ghostly diamond thing. Well, we probably would do better in the future. So as you can see, there are multiple organizations supporting this project and supported in the past, which we are really grateful for. So let's go on. So now so basically this project started in the end of 2017, and so as a hobby, and then it progressed through the timeline. So we have now a much bigger team, and we're hoping to actually make the TurboGeth fully functional really soon, really soon. We're almost there. So some of the people are actually, most of the people that you see on this picture are in this room. You can actually you can raise your hand, guys. Yes. Okay. So sorry. Okay. So now let's. I'm going to try to explain as quick as I can what is the main objective of TurboGeth, what problem it tries to solve, and how it tries to solve it. So let's look at how EVM. So we talked about the state of Ethereum mostly in the terms of the trie, and there's this Merkle tree. But the first insight that you get when you're looking to TurboGeth is that you need to look at it first of all from the EVM's point of view. When the EVM executes things in Ethereum, it doesn't see the trie at all. It doesn't care about the trie. It doesn't care about the Merkle tree, about how this thing's Merkleized. What it actually sees, it sees the accounts with their addresses, it sees their balances with their bytecodes and storage data. And storage data could be represented as well as some sort of mapping. It does not see the storage roots. It does not see the code hashes. Sometimes it's through special opcodes, but generally most of the operations don't care about Merkle trees. It's just this. And this is the main first insight. So the insight is that we only need a Merkle tree when we trying to compute the state root of the state to put in a block header. And that's it. That's the only use for the Merkle tree. And so from this insight, let's see what's the next page. Okay, so this is what I mean by this state root or state hash in the header. So as you see in this picture, these little things on the top are the block headers, and there are 4 important bits of information there, which all of them are 32-byte hashes. Some of them UNCO or OMER hashes, transaction hashes, receipt hashes, and the ones we're going to be talking about is a state hash. So the whole Merkle tree state trie thing is only useful to compute this 32 bytes, and if you're a miner, to put it in the header. If you're not a miner, to compare that what you've got is the same as in the header. And so here, if you have a very sort of simplified representation of what actually happens when you're processing the blocks. So those little stars are, let's say, block execution in EVM. And as input, they take transactions and they take some access to the state, which are these yellow things. And then as the result, they modify the state and produce some receipts, which people can, some people call them logs. I mean, they're logs inside the receipt. And so this one bright yellow thing is the current state. As the block execution progresses, we always have something which is called current state. And this is what EVM sees. EVM cannot see most of those things in the past. It can only see this state. So nothing like that. Again, this is another insight. So if you're asking the question why Ethereum, most of the Ethereum implementation, when you run them in a so-called archive node, why they take so much space, is because they keep all these things in a not very efficient way. So now, okay, so now let's look at how the state root is actually constructed. So we start again with the EVM view. So EVM looks at the accounts or storages as the simply keys and values. So the keys are, so here for the simplification of visualization, I present you not the binary, not the hexary, but the quaternary representation, just to make it more fun. And also not just for fun, but also it's a bit better than binary because it can show you some features. So you can see there's a quaternary keys, and it's the some sort of values. I don't disclose what these values are because there's no space here. So these can be accounts or storage values. At the moment, you can see they're not sorted. Now, first step in order to compute, let's say that this is our entire state, and we want to compute the state root. What do we do? As it's described in the yellow paper, and it's implemented in every implementation. So first thing we do is that we're sorting those keys. I mean, to be strictly accurate, we also have to hash them first, but I'm going to omit this state. Imagine that we're not doing any extra hashing, we just sort them. So next thing we do is that we are making what I call the prefix group. And so the definition of the prefix group is the group of keys that share the same prefix, and there is no smaller group that shares that prefix. So let's take this as an example. These three things, they share prefix 2, 3, and there's no there's no larger group that shares the same prefix. So that's your prefix group definition. And as you can see that we can group everything in prefix groups, and then we can observe that we can combine the prefix groups in a larger prefix groups, like as you can see there. And so that's first step. So it's the second step, sorry. And then we apply what they call optimizations. So in each prefix group, we're essentially taking this prefix out of the keys and move them up. If you compare these two pictures, we move them up, and we essentially where you saw the hierarchy of the prefix group, you can see now these branch nodes. And then having this type of structure, we then apply the Merklei's the hashing. So we start making the hashes of these things, and then we combine them, we concatenate them, we make a hash of this prefix group, and then we do this. We do this prefix group. In the end, we come up with the state root of that stuff, right? So it's just basically what I'm trying to do here is to try to represent you the semantics of the Merkle hashing in a slightly different way, not in the same way as it's written in yellow paper, but I believe this is kind of the more mathematical way to go about it, to introduce the prefix groups. So now, if you look at the Go Ethereum and other clients, what they do is that they take this representation and they port it straight into the database. Because it was the most straightforward way to implement it back then in whatever 2014 and 2015. Just take that, and so the inside here is that, imagine this is the directed graph. So what you saw in the leaves here is these diamonds, and these are our branch node, and pay attention to the arrows. So the arrows essentially, like, imagine if this thing is in memory, the arrows are the pointers. If these things are in database, the arrows are like sort of hash pointers. So what we do here is that each figure here, which has the arrow pointed into it, is addressable. And so when we're addressing something, we just point an arrow into it. And in this representation, an address of certain object is the hash of its ROP. That's the address. And then when we refer to it from other element, we use that hash as the pointer or as an address. So that means that we can represent this structure on the left as the database layout on the right. And if you want to calculate how many records do you need to figure out the number of these blocks which have arrows pointing into them. So if you count them, you will get the same number as the number of records here, because each addressable block is one record. And that also determines how you traverse this tree. You start from the, so if you want to access, let's say, V4, and you start from knowing only the root hash, first you use the root hash as a pointer, and you're trying to dereference this pointer to find the object by using address, and you end up reading this record on here. And once you read this record, you will get this representation, and you will be able to deserialize this object, this one. And then once you have that, inside this object, there's 3 other pointers, which each of them is a hash, and you use the same process. You kind of know that the address of this element, like in terms of key, and you know that you will need to dereference the 4th one. And then you repeat the process until you get to the V4. One thing to notice about this process is that there is a data dependency in this navigation. So you cannot dereference this bit until you dereference both of these bits, because you don't know its address. And that means that you cannot parallelize it. It has to always happen in sequence. And it also means that the deeper your data is, the data are, the longer it takes you to access it. So the depth matters. And this is one of the reasons why here I kind of skipped over this fact that usually you don't start with the actual keys, but you start with cryptographically hashed keys, because then it gives you some sort of like randomization and a balance, so that the adversary cannot create very deep trees, so that you will pay the price of accessing them all the time. Now, this is how most of the current implementations store the history of state. Well, that's not it. It will be on a second slide. But let's imagine the 2 blocks. This is our genesis block, state with 3 accounts, A, B, and C. And in the first block, there's a miner E who mined the block and get reward 2 ETH. And there's a transaction sending 1 ETH from account A to new account D, which did not exist before. Miner also didn't exist before. And so in the second block, there's an empty block, but just with a mining reward. And as you can see here, how the state changes, here we add a new extra leaf, and so you get a slightly larger tree. And so here you see the A prime, which means that the value of the A has changed because it deducted 1 ether from it. And then again, here we have an E prime, because the E has changed, it's got now 4 ETH. So, and if you were very naive, you would apply the same principle as before, and you count number of blocks which has arrows pointed on them, which are the addressable elements, and you would conclude that you would have 16 records in the database. Is that right? No, because as you might notice, that there is some deduplication could be made. So you might observe that certain things did not change from one block to another, for example, B and C. So instead of copying the same records, you can just refer to the same records by their pointers. So we arrive at the number 10. So this is how the historical state is now stored in most implementations. I mean, I'm pretty much can say all of them in C, but just to be cautious, maybe somebody secretly developing something else. Right. So now this is where we're going to talk about what we do in TurboGeth instead, how we're going to improve the situation. So I have crossed out the Patricia tree word. Remember our insight that we only need Patricia tree and Merkleization only to compute that state root. So what if we separate these two things? So in TurboGeth, we store the data in a much more straightforward way. We do not try to mimic the structure of the Merkle tree. We make it optimized for EVM rather than for Merkleization. And Merkleization, we solve it as the side problem that arises later on. Okay, so we're saying, okay, this is how we're going to do it. We're going to optimize for EVM, and let's see how we can figure out the Merkle root problem. So in this case, let's say that we wanted to access these bits, and they imagine that they're not in the memory at the moment. We have this thing in the memory, this thing, but not that. And what we do in TurboGeth, we know that all these things, because it's a prefix group, they will start with the prefix 0. And so we do range query to the database, actually not 0, 1, because I make it more for the usual humans, not for the programmers. So it starts with 1. So we know it's a prefix group, so we query from anything which starts from 1. So at the end, we get the 2 results, and then using some, the algorithm which based on those prefix groups and stuff like this, we can reconstruct the entire piece and plug it into our tree in memory. Okay. So that's what we do. Now, when we store the history of state, we also do it in a different way, of course. We have the notion of the change set. So when in TurboGeth we process the blocks, we basically now making it into the multi-stage process. So first stage, we are computing the change set. We are computing everything that has been modified, all the accounts and all the storage items that have been modified in this block, and we actually sort them and we place them in a special place, in a special bucket in a database. And then other things like Merkle, like a witness creation and other things, you can actually use that. And so our history is mostly consist of the change set. So every time we process the block, we generate the change set. So for example, here we know that accounts B and which one is E and D did not exist. So therefore, in this change set, we are saying that they have 0 value. So the change set, this is an important thing here, is that they tell us what the values were before the change, not after the change. So that's the crucial thing. So we say that here is A not a prime, because the change set tells us this was the value of A before we changed it. And the reason why we do it is because if you were at this point, after you've just executed block 1, you already have A prime in your current state. Why do you have to store it again? But it is interesting what it was before. In the same way, these things just appeared, so we just mark it as empty so that they have just come to the state at this point, and so forth. So, and then the change set are good when you, for example, want to do the rollback and stuff like this, but they're not so good if you, let's say, if you're now 1 million block later, and you're asking the question, but what was the balance of the account A at the block 1? What is it? You don't want to go through like a lot of change sets. So for that reason, we have a special index, which on the which I show on the left, that for each account will contain the basically like the time series, the list of numbers where in which blocks was this account modified. And this is what we call now the thin history. It's one of the latest projects we are finishing off. And when I said it's going to be ready soon, so this is one of the things that we have to finish before we ship, before we release the first client. And it has a lot of promise because, so this is a courtesy of Boris, who produced, I think, this graph. So this is actually 652 gigabytes. So some people will call it archive node, but I don't want this terminology because you can now you can pick and choose what you want in your node. And so this is the maximum. Like if you turned on everything that you record everything that is possible at the moment, and then you synced it to 24th of January this year, you get 652 gigabytes. And then with the thin history is the change that we're testing right now. You observe the difference in multiple places. So we removed the receipts, unfortunately, here. So disregard this. Receipts will still need to be enabled. So that was we just didn't have the data with the receipts. So, but you see that here, the change set is split into 2 logical pieces for accounts for the storages. You might, if you're good with maths in your head, you might figure out that this number is actually, the sum of these 2 numbers is less than this one. Can you figure it out? Now, you also observe that the big difference in history of accounts, because these things are now just indices pointing into the change set. And previously, they were essentially duplicating information with the change set. But that's basically, the current state. So it's one of the projects we're finishing off. Another project that we're finishing off is solving another issue. So this is, I'm going to show you what the issue is. And this is the currently my personal main criticism of TurboGeth. Why I think it's not ready for prime time yet for lots of use cases. So imagine this is, so here for simplification, it's a binary tree, it's not hexary, but it will be easier to explain you what I mean. And imagine this is our entire state, like 32 things, yeah. And because TurboGeth does not store the hashes and stuff like this, it only stores this bits. Imagine we shut down a node and we bring it up again. And we do need to start verifying the state root. So what do we do now? Well, we're going to read out everything, all the state, the entire one, the entire state, which currently is about 32 gigabytes, which takes, well, and depending on your hardware, might take anything from 1 hour to 5 minutes. Best hardware, you can read it in 5 minutes. But the thing is that you read it very efficiently. You just read it like through it's all together. It's not like you have to search for it in a random space. Anyway, you read it, and as you read it, we have a efficient algorithm for not buffering it all, but we on the fly, as we read it, we actually compute the state root, and we also keep certain number of top elements up there. So we spend a lot of time optimizing this kind of stuff. So we're very good at reading pieces of state and hashing them and only leaving the things that we need. This is all kind of been worked out. But still the problem is I don't want to wait 1 hour or whatever, 10 minutes to start up the node. I want it quick. So now what is the problem? Why? And the second part of this problem, imagine this is our cache. So we obviously, if we have RAM, if we have some RAM, we would use it to cache some of our state tree so that it is quicker for us to do the state root. And imagine this is our current cache. So this is what in the memory, and some transaction comes in which accesses the cold data, which is not in a cache, needs this. So how are we going to get this? So this is how we do it at the moment. We have to issue this range query. Remember that was range query because we know this hash corresponds to a prefix group. We know the prefix. We issue the range query for all the entries with this prefix. We read them all. We use our super duper efficient algorithm to hash it, but still you have to read all of these entries just for the purpose of accessing one. And that's the inefficiency. Then what we do is that we discard as part of our efficient algorithm, we discard those things as we go. And what we're leaving in the cache, which is now hot because it's been accessed, we leave in these things some ziblings and some of the hashes. So that helps us to compute. Let's say if we modify this, this will help us to compute the state root after the block execution. But it's unfortunate. I think this effect, so as we saw before, the first effect means that the startup takes a long time sometimes, but this also means that after you've started up, your first, let's say, 10, 20 blocks are getting really slow because there's a lot of cold state. You have to keep fetching it until your cache grows to reasonable size so that you can go it faster. So it goes like, you wait like 10 minutes for loading up the initial state, then in the first block takes you 1 minute, and the next block is 30 seconds, and then it goes on, and then in the end it's like 100 milliseconds. We want to fix this. Oh yeah, and then the next step is that because your cache is limited, you evict something. So something which hasn't been accessed for a long time, we evict it, and these things will be replaced by, sorry. Yeah, we evicted essentially, then we're gonna just replace it with the hash in there, but I didn't show it in the picture, sorry. So now now to the solution. This is one of our other project which we kind of coded up, but we need to debug it. So the idea is that we're going to start actually storing some of these hashes that would have been in a tree if we were Geth or Parity, but they're not. But still we're storing them by using prefixes again. So the key in our database will be prefix, and the value is going to be, yeah, the prefix and the hash. Yeah. So now let's look at our situation again. Again, the same exact problem. We have this kind of cache. We need this element, but this time we also have some intermediate hashes stored in the database. So the way it goes this time is that, okay, we are going to read only this amount of information, only 4 entries from the database. We're going to reconstruct the tree, and we will be much faster. And as you can imagine, that this will also speed up the startup process, because it will not need to read the entire state database. And there are nuances in this. For example, we decided not to keep all the intermediate hashes, but only those that were, you know, like if you, let's go back to this. So here, this is a binary tree. So it means that if you have a key goes all the way down, each level is 1 bit. 1 bit, 2 bits, 3 bits, 4 bits. So if you look at this one, it will have a prefix of 1, 2, 3, let's say 4 bits, right? And then another one will be the same one, but the 5 bits. So how do you distinguish between something which is 4 bits and 5 bits if you always store them as a byte? So we had this problem, and we just decided, okay, let's not store any intermediate hashes whose prefixes are not whole bytes. We're just going to do whole bytes. Like if it's a binary tree, we're just going to store them for every 8th level. If it's a hexary tree, we're just going to store them for every 2nd level. So in this case, all our prefixes are always whole bytes, and we should be okay. We still have to test the performance, but we think it's going to be enough. It will also make it easier for us to transition from hexary to binary trees, because we won't need to do special logic for that. And that's the first nuance. The second nuance that is that we are not keeping the intermediate hashes of the things which are in memory. So going back here, so if this is our cache, we do not store any intermediate hashes in the memory in database, because they're because they're in the memory. So we always have this invariant. If something is in the memory, it's not in the database, and the other way around. Which if you give it a little thought, you think you understand it makes sense. But that's what we do, and that's how we prevent like a thrashing of the database, because the root of the tree will be the most modified. Like it will be modified all the time, and you don't want to rewrite your database all the time. So we say if it's in memory, we don't touch it in a database. It's not existing there. And one of our biggest issues is the create to, has always been for TurboGet, because it allows you to recreate the contracts on the same address, and there's lots of pain in this, but we are going to be fine. We're fine. You know, it's a hard problem to solve, but yeah. Now, oh yeah, there's a baseline. So we haven't produced the performance metrics on the intermediate hashes yet, but we will soon. And this is what I was trying to figure out recently. I was trying to see where we're gonna go. So this is kind of a bit confusing, but I'm going to explain you as much as I can. So the red line is the time in the millisecond that TurboGet is spending to simply execute the block. So let's take all the transactions, run through it with the cache of, let's say, 1 million nodes, and just execute it. And sometimes when there's a cache miss, it goes into the database, but the database is optimized for this kind of thing. So then the resolution, the blue line, it corresponds to, so the resolution corresponds to this process when we are missing something and we need to load it up from the database. So in some, there will be multiple places in the state where we have to do it. And the entire process in total, I call it resolution for historical reasons. It may be a very confusing word, but it's a blue line. So you see, it's like a fluctuating. With the intermediate hashes project, we're hoping to reduce that. We just bring this blue line down and make it less volatile. We don't have the data yet, but I hope it will be somewhere there, right? And then the yellow line is, what is it? A stateless execution. Oh yeah, this is actually very rough data. it's just for fun to put here, like, how long does it take currently for TurboGeth to ingest the witness for that block and execute it statelessly? At the moment, it takes longer than executed non-statelessly, but we always say that it will be optimized. And the other lines are just essentially the orange one is that once you've finished execution of the block, once you pulled up all the necessary data, how long does it take you to recompute the state root? And it's currently like about 10 milliseconds. Yeah, and then the green thing is another experimental feature, is that what if we did not need to modify the trie to compute the state root? How long this is going to take? I'm not going to try to explain what it is, but this is used in our mining engine, because when we turn the mining engine in TurboGeth, we basically have only one single copy of the trie in memory, and what happens is that the mining engine usually competes with their usual execution, because it produces what we call speculative blocks that would mine. And usually, if you're trying to mine a block, they would try to disrupt your trie, which you're using for your other blocks. And in order to prevent this, we have this logic where you can compute the state right without modifying the tree. It's an interesting and involved process, but this is the green line, and I'm also trying to bring it down so that we can potentially swap it. We can remove the orange and put the green instead of it. And so we have it, we make it the normal mode of operation. We always first compute the state root, and if it's correct, only then we modify the tree. Otherwise, we just don't touch the tree at all. And it will help us with some situation when we get invalid blocks. At the moment, TurboGeth suffers if you give it invalid block, which is valid in terms of proof of work, but it's invalid in terms of state hash. It has to flush all the cache from the tree because it's corrupted, and then basically rebuild it again. So we're hoping to remove that problem with this green thing. Okay, that concludes my part of the talk for stateless client. I hope you're not too tired yet, because I'm going to go on for another 20 minutes. All right, so I'm going to take all the questions in the end. I'm hoping to get through this very quickly, because I think it's just only 5 slides, and a lot of things have been said before me. I'm not sure if I'm going to bring you any more new information here, but essentially, if you remember my previous picture about the block execution, this is a slightly modified version. You might remember that in the previous picture, we had the states here, like a yellow bit, which were representing the pieces of the state, and then there was another big yellow bit here, which is the current state. What has changed? Those things disappeared, and as it would in a stateless client, and instead, instead of just receiving the header and the block body, you're now also receiving as a package the block witness. This is looks like some kind of building, but it's actually block witness, and you understand why a bit later. So what we're doing now is that we don't need to look at state. It's enough for us to look at all this information to make execution, provide the receipts, and verify that our the state root matches. I think it's that one on that one. No, that one. Yeah, matches the state root in the header. Okay. And it answers the questions that were asked before, that it is full validation in that sense. Okay, so now you should understand why there was things like a building in that picture. So I did this visualization, which some of it Sina used probably that part of it, and he also kind of rotated it 90 degrees clockwise. So you might remember that bit. So it's from the same block. So we found this relatively small block on the main net, which was that 5.7 million. And it was good because it only had 2 transactions, and one of them went to a contract rather than just a... So yeah, there was one transaction which went to a contract, which then created this blob here. And another transaction simply moved Ether from one account to another. And as you can see here, because we touched that contract, we invoked it, and it probably touched some of the storage. So this part of the trie, the witness, which is actually part of the trie, is account. So do you see this little you see these vertical things are the accounts. So, and these things are storage items. And this is the contract code. And this is actually demonstrates another thing, which some people who are familiar with Ethereum implementations, they know that in most of them, there is a certain, like, these entities are separate. There is this account trie, and there's a separate storage tries. What we have done in TurboGeth, we have actually merged them into one single trie. And the way we did it is actually quite simple. We just introduced a new type of node in the tree, which is called account node. And that is the connective between this trie and all these tries. We just basically simply hang the storage tries onto these account nodes. It works brilliantly. And it also helped us to do witnesses regardless of whether they penetrate into contract storage or not. They're just one thing, which you can assemble from the input. Okay, so I hope that picture demonstrates you how many hashes we've got, because we have a hex array trees in lots of positions. We have almost 15 sibling hashes. Yeah. Okay, just for 2 transactions. Yeah.
It's the reason why the merchant found the price storage.
No. It was the reason why we merged the accounts and storage is because it made our code simpler, and then it happened that it made the witness production simpler. It was simply just some logical thing, some logical refactoring that seemed to be like naturally occurring, like it naturally falls out of what we wanted to do. Yeah, but I think you might be right. It actually did occur when we were trying to fix the create2 problem. I don't know, I don't remember exactly how, but it happened during this change when I think Boris was trying to do this. We were introducing this concept of incarnation, especially to support create2. And then during this huge pull request, we have merged the trees and stuff like that, and then it stuck, and it turned out to be quite useful thing to do, like to just put them and everything together. And it will become useful when we go into the snapshot sync algorithms, because you don't have to treat them in separate ways. You can just look at this whole thing as one big blob, and then you just sync it. Okay, let's go on. So people were showing different graphs before, but this is one that I produced. So, so in this graph, which is actually pretty old, you see we're now almost on the 9.5 million. But what it demonstrates is that, like, this is the size of the witness with some sort of moving average starting from just past the Shanghai attacks. Because if I showed you Shanghai attacks, it would be like over there on the ceiling, probably, maybe, yeah, something like that. So, but these are the kind of something that was said before by Sina. The blue portion is the hashes, which you could see in the previous slide. The red portion is the bytecode. The yellow portions is the leaves. Those were these kind of things are the leaves. These are the leaves. And what is another one? The orange portion is what I call the structure. So the structure is the extra information that allows you to take all these things and connect them together in the correct way. So instead of having like a big soup of hashes, big soup of leaves and everything else, so how you take that and connect it all together into this particular structure that is, so that's what I call a structural information, and it's orange. It's not significant. So this explains why we're looking at binary trees first, because it addresses the biggest thing. And so what Igor discovered, that if we do that, this will shrink like 3 times. And when it happens, the red thing will become dominant, and that's why we're attacking that second, and that probably would shrink. I don't know what the number is now, but shrink further. It's no point looking at these things yet. And therefore, when people say that, okay, well, you know, what about different types of witness encoding? I said, it's not really important right now, because that is just really tiny compared to everything else. This is not the biggest problem we have to look at. So we can make the modifications in the structure, you know, they will not affect that much. and we get into almost to the end. So this is the graph that Igor produced, which kind of reinforces what I said before. And the blue line is the current sizes. I think these are the megabytes. This is the correct thing. The moving average, and this would what it would look like if it was a binary tree. And then this is a repeat of the CNES slide. I'm just gonna. So here we're just gonna say that I would like to make the Merkleization of code oblivious to what the code means. So I now start to call it oblivious chunking for various reasons. And I think we have even just yesterday, we had some interesting insight about how to do it even without doing static analysis. But I'll write it down later. We just were talking yesterday, sitting in the at 9:00 p.m. sitting in the hotel in a lobby with Igor, and I was trying to explain what is the problem with this job destination. And after that, he said, okay, but why don't you do this way? So what he essentially proposed is to include the list of job destination. I'm sure we talked about it before. Include them into the Merkle tree, but we'll see that later. So now did I already start talking about reduction strategies? Yes, all of these were reduction strategies, yes. So sorry, I didn't announce this switch. Obviously, the size of the witness is one of the biggest problems, and so therefore we're looking at different reduction strategies, and the first one is the binary to hexarray to binary. Second strategy is the code Merkleization in the matter of priorities. And then there's another strategy which is non-consensus, which that's why I underlies, because Vitalik wants to stress this out for everybody. This is not, this is average case optimization, or maybe even like most case optimization. We might not be able to use this to base our gas pricing on, because there will be nodes which have no caching. So what this basically picture shows that if you have this size of the cache, if you have like 1 million nodes of the state trie always present in your memory, and you are using LRU eviction policy, then you will not need to see most of the witness. You will only need to see the witness which you don't know yet. So if you go back to this picture, if you have the very large cache of this stuff, most of that information that you receive, you already know. It's already going to be in your cache. So what we're doing is we're taking that out, and we're only leaving out the information which is new to you, and we're measuring how much is this going to be. And with this particular like magic number, 1 million, and it turns out to be quite a significant drop. We haven't tested it on different numbers yet, and that's another topic of research. But anyway, so and then there's more. There's another reduction strategies which we discussed a little bit yesterday. We can use some sort of CIP, computational integrity proofs, systems like Starks and Snarks, to remove intermediate hashes. So at the moment, we're not actually pursuing this. We did some preliminary research on this. We realized that it will require some fair amount of professional work. If we did this work, we would probably need to spend like at least a year on doing this. If we hire some professionals, it will be shorter, but they will have to take it out of their sort of revenue generating projects. And yeah, currently it doesn't seem feasible at this point, but if the project gets more traction, we might be able to justify taking those professionals out of their projects to help us. And there are some other like edge case complexities which were discovered. Yeah, you need to have 2 proofs before execution and after, because if you remove the intermediate hashes, you lose the ability to compute the resulting state root, because you simply don't have the hashes to do that. So then in this case, you have to be proven twice. You have to be proven that this is the data that belongs to the initial state root, and this is the data that is belonging to the resulting state root after the execution. You also need to specially include the proof of non-existence for certain things. interior. Well, it's not hard, but it has to be said. And also it makes it harder to split the witnesses into pieces. Although some people may point out that looking at this picture, you know, what we're talking about, if we remove this blue line and reduce this, basically the CIP approach removes the blue part completely and replaces it with a fixed size proof, then, you know, do you really want to chunk the remaining things? But maybe you do. But I needed to put that on a list anyway. So this is for completeness, and I think that's the last slide. Thank you very much, and I will take any questions now.
Your optimization is a good one to keep caches, many caches in RAM, but you said you keep about 50% of caches in RAM only at byte boundaries, the ones that are the second byte of the second nibble of the bytes. How many caches, is the question to think to, how many caches, how much RAM you need to store all of this, and at a certain point?
You're referring to this, right? To the intermediate hashes thing?
Another slide after that. Yes, this one.
Yeah.
The blue one's in RAM.
Okay, no, blue one's not in RAM. So here, okay, let's me talk about. So the blue things, the intermediate hashes, they are not in RAM. They're only on a disk. So when they get into RAM, I delete them from the disk. So this is actually interesting. So when I utilize those things, so they're currently in the database. They are the thing I have in RAM is this, only that root. So those things are in database. They will help me to fetch this element with the proof without reading everything in vicinity of this element. But once they've read them, what will happen? So I'm sorry I didn't make it clearer. So let's say that we have used those light green things to fetch this, to using only 4 records from the database. At this point, I will remove those things from the database because just in case they are modified, they will be inconsistent with the database. We basically ensure in the consistency by always removing things from the database that we read in memory, and the vice versa. We are putting them in a disk when we unload them from memory. So when we evict something here, when we evict, oh no, where was it? Eviction thing. Yeah, so let's say that we evict this in our ideal scenario. When we evict things, we actually add those intermediate hashes into the disk because we know that this is now cold. We have to provide some extra stuff so that we can fetch it quickly later. So, and that means that in order to modify anything in our scheme, you have to first load up in the memory. So when you load it up in the memory, you remove it from the database, and that removes any possibility of inconsistency. And another reason why we can do that is because we use ACID transactional database, which would allow us to do these things very easily. We simply bind all these removals, additions with the same transaction as the basically modifies the state and puts the blocks, and we have a guarantee from the database that they either all succeed or all fail. So we cool with that. It will be much harder to do that with the things like level DB, I would say, because you might be stuck with some inconsistent hashes in your database which you didn't remove because the light turned off at that point or something like that. Yeah? This is the person who is implemented this, by the way.
A question about another thing. You mentioned that in the previous data layout, guys hash keys to add some randomization to protect from attack, which will make 3-2D.
Yeah. Yeah.
But you removed hashing, and so removed some randomization. How you plan to protect against the same attack or against the attack which try to make your tree unbalanced?
Okay, so we not removed this bit. So in in all the implementation, including TurboGet, the keys are still hashed before they are logically or physically added to the Merkle tree. When we store them in a database, even now we're using hashes of the addresses rather than addresses. And the reason why we do that is because if the Ethereum yellow paper, whatever, did not require us to pre-hash the keys before we add them into a Merkle tree, then of course we would have preferred to just store addresses and the storage locations. But because we have to then use those things to compute the Merkle tree, it just becomes much more easier. It becomes easier to store the hashes of addresses. You might notice that everywhere we just use the hashes of addresses instead of addresses. It confuses a lot of people, but that's unfortunate reality. So we're not removing that. No, we're keeping that because it's a consensus agreement. It's like it is how you calculate the state root. Guillaume? Yeah. Microphone.
Sorry, but you still store the prefix of the tree in not hashed way.
So the prefixes refer to the prefix of the hashes, not to the keys. But I just wanted to make it easier for you so that you don't have to deal with the cognitive load of remembering about hashes. So that's just simplified representation. I thought it was.
Yeah, no, it's a very general question. You know, a couple of days ago, Vitalik, I think, talked about his one of his EIPs where he wants to merge the account trie and the storage tries.
Okay.
I was wondering, how would you update your like? How would that affect your implementation of rebuilding the?
I don't know how he wanted to do it, but I don't think that we will have to change much. Because from my point of view, we don't even need the IP to do that. It's just implementation detail. I don't know. Maybe there is a reason why you have to do EIP for that, but we just implemented it.
If you store the values under the hash in the account tree, so like the main tree also like has the hash of the account addresses, but also hash of the storage keys of the contract.
Yeah. Well, basically, the argument here is that the hash of the storage keys of all the storage subtrees could be looked at in the same way as you look at these intermediate hashes, right? Like I could even in the future remove those storage roots from the accounts because I have these blue things. And the blue things will be exactly what I need instead of the storage roots. So what I'm saying is that to me, it's implementation detail. You can do it if you want to in any implementation. Maybe there's something interesting that in IPS. So but I'm sorry I didn't look at it. Yeah. Yeah.
Slides towards the end where you said the tree structure is very small relative. You can see that on the.
Oh yeah.
That one.
Okay. This one.
Yeah, so it looks negligible. The yellow is...
Yellow is the leaves, and then...
The structure is orange. Okay, so the structure looks like it's almost nothing.
Yeah, so actually, I think this graph was done with the even like really old version of the structure. I didn't bother to update it because it doesn't really matter too much anyway, so... it will be maybe now the structure becomes slightly smaller.
Okay, slightly smaller relative, but this is, you know, visually, someone can see that that's huge and that's almost negligible, so it's not worth looking at. But this is for the hexary case, and now we have a binary optimization. We might have some more optimizations here and there. And the orange relative, you know, visually, it might be relatively bigger.
Yes.
So what is significant? 5%, 10%? At what point do we think that the orange is significant relative to
I don't know. I don't have this threshold. But there's another interesting thing is that when we go from hexary to binary tree, the structure will also reduce a little bit. And the reason for that is because currently in the unfortunately I cannot zoom it in, but if you look at those things, there's like little like horizontal bars. What they represent is these 16 nibbles from digits from 0 to F. And when we encode this witness, we need to take into account that sometimes there's not all 16 of them are populated. Sometimes there's 14, sometimes there's 13. And so what we do is that we add a special mask that it could be represented in 16 bytes, but sorry, in 16 bits, but we do it in 1 byte, which tells us like how to position those as children. In a binary tree, as you might imagine, there is no such need because you always have exactly 2 children. So you don't have to actually specify this. So there will be a slight reduction in the structure.
But you will need 4 times as many branch opcodes.
Correct. Yeah, sure. Actually, that's interesting insight. Maybe we should look at these orange part in the binary trees. Yeah, we could do that.
Unfortunately, we are running out of time. So thank you very much, Alexei.
Well, we can take it. We can take it outside. I think because there might be some other talks happening.
The second byte actually hold the mask. So, for example.
Yeah. Okay. We can take the discussion outside of the room if you want.
Thank you very much.